So today I'm going to be talking about black box variational inference and how we can make it faster and more effective. What we'll see is that by utilizing the structure of the variational family and using something called score matching, we can derive algorithms that are in some cases orders of magnitude faster than stochastic gradient descent. And so this is joint work with my collaborators, Chirag, Lucas, Charles, Robert, David, and Lawrence. All right, so let's start with a motivating example of designing photovoltaic materials. So these are materials that take in energy from the sun and convert them to usable electricity. And so in order for these to work well, we'd like them to have certain properties. For instance, we'd like them to absorb the right parts of the sun, convert energy efficiently, and remain stable for decades. And so a common alloy system consists of copper, indium, gallium, selenium, and you can imagine also adding other elements to this combination. But very small changes in the composition, for instance, the ratio of copper, can dramatically affect the performance. And so how do we know which combinations we should try? So traditionally, discovering new materials has been slow and costly, relying on a lot of trial and error in a lab. But what if we could predict how materials behave before we ever create them? And so there's a huge opportunity to design computational methods to accelerate this process. And so in a nutshell, the properties of a material depend on how the atoms are arranged in space, which in turn determines the free energy, a quantity that tells us about the stability and functionality of the material. But there's two big challenges. One is that we have a very large design space that we can't possibly search exhaustively. A second challenge is that these free energy calculations use costly first principle calculations that could take many hundreds of hours to run. So the way we're going to address this today is by taking a probabilistic approach. And this allows us to reason under uncertainty and make better decisions. So the idea is to, we can then run these expensive simulations for individual alloy compositions, but that the full energy landscape is unknown. And so instead of doing a brute force search, we're going to build a probabilistic model to predict this energy. So for example, we could model the energy as a function of the composition X using a Gaussian process that depends on some kernel and some kernel hyperparameters theta. So here's just an example of the model after observing 3 data points, where this blue curve represents the predictive mean of the model and the shaded regions represent the uncertainty. And the black curve here represents a realization from the model of a potential energy function. So once we've specified the model, there's a number of inference problems that we might consider. For instance, what is the energy at unseen compositions? And also, how do we learn these kernel hyperparameters theta? And after we do this inference problem, we still need to decide which alloy composition to evaluate next. So this is often encoded by an acquisition function that determines the value of new observations. And in particular, making good decisions relies heavily on good and reliable inference. So here I'm showing many examples of acquisition functions using different hyperparameter learning strategies. So in particular, the maximum of each curve denotes the next composition to evaluate. And so the black curve here represents what we would get if we knew the true hyperparameters. The blue curve is what we'd get if we plugged in the maximum likelihood estimates for the hyperparameters. And finally, the orange curve here represents a probabilistic approach where we've averaged over many acquisition functions using hyperparameters sampled from some distribution. And so there's many desirable properties we'd like our inference algorithms to have within an active search algorithm. One, we'd like them to be fast in that the cost of inference should not dominate the cost of each energy evaluation. And two, we care about accuracy in that poor uncertainty on quantification can lead to bad decisions and therefore wasted resources through expensive simulations. So here's an example of the sort of distribution that we're sampling from. And this contour in blue represents this posterior distribution over the hyperparameters. And what we have been sampling from is actually an approximation of the posterior using variational inference. And indeed, variational inference algorithms can often result in fast ways of doing approximate inference. However, as we'll see later, optimizing richer approximations under these computational constraints can be quite challenging. And so this isn't just a problem that we encounter in materials. This happens in a large number of scientific domains, from probabilistic inference of biological networks to parameter estimation in astrophysics. And one of the types of algorithms that we're really interested in developing are black box inference methods. So these are methods that do not make model-specific derivations, making them easily applicable to generable models. In particular, black box variational inference algorithms can converge very slowly due to things like noisy gradients, sensitivity to learning rates, and other parameters. And there are going to be additional challenges in the optimization that result from using richer variational families. For instance, when we go from a diagonal to a full covariance Gaussian, the problem gets much harder. So today's talk, I'm going to introduce a new way of doing black box variational inference that I call score-based BBVI. And essentially, it's going to compare the scores of our variational distribution Q with the scores of our target distribution P. And what we're going to see are several things. One, by using the structure of our variational family, we're going to be able to avoid noisy gradient-based optimization. We'll also see that we can apply these methods to richer variational families, such as full covariance Gaussians and families that come from orthogonal basis function expansions. And finally, we'll see that this often results in much faster convergence, sometimes several orders of magnitude faster than stochastic gradient descent. So in what follows, I'm first going to tell you about what is variational inference and black box variational inference. I'll tell you about score-based variational inference and talk about developing these for full covariance families and then orthogonal basis function expansions. OK, so in our problem, we're interested in approximating some target distribution over latent variables. So I'm going to denote this by P of z. And we're going to assume that this is something that we both cannot sample from, nor can we evaluate it. So oftentimes it has the following form where you can write it as this unnormalized density rho of z, and then there's some intractable component c. So for example, in the context of Bayesian inference, this rho of z often represents a joint distribution between your latent variables and your data. And so what we do in variational inference is we first pick some tractable family of distributions Q. For instance, a Gaussian with diagonal covariances. And then what we do is we choose some divergence. Most commonly is the KL divergence. And we try to find the member of the family that minimizes this divergence. And finally, we'll approximate our target distribution with this optimal variational Q star in downstream tasks. So for example, here I have a picture of a target distribution on the left, and on the right we have the approximating distribution from variational inference given by a diagonal covariance Gaussian. So in black box VI, we typically don't want to make assumptions about the target distribution other than, for instance, that we can compute the score. So this is the gradient of the log of the target, which is usually available to us through the unnormalized density rho of z. And what is most commonly done nowadays is stochastic gradient-based optimization of this KL divergence, or also known as sort of the elbow. And this leads to algorithms that are very popular, such as ADVI, which stands for automatic differentiation variational inference. And so, thanks to advances in automatic differentiation, black box VI is now widely available in a lot of probabilistic programming software where practitioners can apply them to a wide host of models. So why do we want to do score matching? The idea is we want to compute scores, or the gradients of the log densities. And this really naturally fits into this black box sort of nature, because we don't need to evaluate the target directly. We just need to access it through its score. And so a question is, how do we make the scores as closely as possible given a set of samples? So here I've depicted a log density, and what we want to do is look at a bunch of samples from our latent space and try to find the member of our family that matches the density at those scores. And so what we're going to do is formulate variational inference using a score-based divergence. In particular, in this current discussion, I'm going to assume that our variational family is a full covariance Gaussian. And we'll define the following divergence to measure the agreements between the scores of our variational density Q and our target P. It looks like the following. So it's some sort of expectation over Q, and of the difference in the scores of Q and P. And here you note that this norm here represents that we're going to weight the norm by the covariance of Q. And so this is, for this reason, this divergence is often known as the weighted Fisher divergence, in particular weighting it by the covariance of Q. And it has a number of nice properties that you would like a divergence to have. For instance, it's non-negative with equality if and only if P equals Q. It also is invariant to affine transformations of the input space. And this property turns out to be very important because it leads to closed-form solutions when we try to optimize the divergence. And this is actually not true if we did not have the covariance weighting. So, how do we optimize this divergence? For those of you that have heard of the reparameterization trick, this would indeed apply here as we're working with Gaussians. And we could go ahead and use SGD to optimize it. However, you're going to end up with the same sort of issues that you encounter with ADVI here. And so we're going to take a different approach. So instead, what we're going to do is the following. So suppose we're trying to minimize this divergence, and we can't compute the expectation, but we can take samples to compute a Monte Carlo estimate. So it has the following form. The issue is that we're now trying to optimize and sample from the same distribution, which is something we can't simultaneously do. So we need a way of decoupling them. So what we'll instead do is formulate this iterative procedure where we start at some initial variational distribution and we try to get closer and closer to our target. And what we'll do at the tth step is sample from the current variational estimate, Q of t, to form our estimate of the divergence and try to minimize that instead. So this is going to introduce some bias. So we're going to add some regularization to our score-based objective to ensure that we don't move too far from Q of t. So we'll add some regularization term. In particular, what I'm describing is also called a proximal point algorithm. And in our particular problem, the global minimum of the subproblem can actually be solved analytically. And so this brings us to our actual algorithm, which we call batch and match variational inference. And it's going to iterate between two steps, a batch step and a match step. So in the batch step, what we'll do is, given our current variational estimate, we're going to sample a batch of points, z1 through zb, where capital B here represents the batch size. And we'll compute this empirical score-based divergence on this batch of points. Then we'll do the match step, where we fit a new variational distribution, qt plus 1, by minimizing this regularized score-based objective. So here, the first term represents our empirical divergence, and the second term represents a KL regularizer between qt and q. And finally, we have this inverse regularization, lambda t, which can be thought of as a learning rate, because when lambda t is very small, the regularization gets big, so it encourages our step sizes to remain small. In particular, this proximal point update has a closed-form solution. When our family is Gaussian with full covariance sigma and mean mu, we can compute the following updates. For the covariance update, it arises from solving a quadratic matrix equation of the following form, where UT and VT are matrices that depend on the current value of the covariance and statistics of the batch and the scores. And you can see our paper for actually solving this equation. The mean update looks like the following, where we take the current mean and we add something that depends on the mean of the scores computed on the batch of samples, and the current covariance update. So therefore, it's very important to perform the updates in this order. And the computational cost of these updates is naively going to be d cubed. But if the batch size is smaller than the dimension, we can come up with a low-rank update that is essentially making the computational cost d squared. So now I'm going to talk a little bit about the convergence properties of this algorithm. First, we can look at the theoretical properties. And this is in an idealized setting where we assume that the target itself is Gaussian and that the batch size goes to infinity. Then what we can show is that for any learning rate, the BAM mean and covariance updates converge exponentially quickly to the target mean and covariance. And it does so at a rate that depends on the initialization and the amount of regularization. And so some remarks about this result. One, theory for ADVI with Gaussian targets assumes a particular tuning of the learning rate. And in our case, we can actually show that it holds for any learning rate. And then also, while our results are assuming this infinite batch limit, we do observe empirically for finite batch sizes that we still get rapid convergence when the target is Gaussian, even for very small batch sizes. So here in each panel, I'm showing Gaussians with an increasing number of dimensions, and the batch size is denoted in the label. And the x-axis here represents the number of gradient evaluations, and the y-axis here represents the reverse KL. For non-Gaussian targets, we also tested this empirically, and we see sort of similar behavior. So here, what we're measuring instead is the relative mean error that tells us how good is our variational estimate of the mean relative to the MCMC estimate of the mean. So in all of these plots, these dashed lines represent a smaller batch size of 8, and the solid lines represent the larger batch size of 32. And we can see that by utilizing these larger batch sizes, we're able to achieve faster convergence than the baseline methods. And the second one is just a latent Gaussian process model that is very similar to the model I'm using for the materials problem. And again, we see the same sort of behavior that BAM can utilize these larger batch sizes to converge faster than the baseline methods. So next, we looked at a higher dimensional application arising from deep generative modeling. So here we have a data represented a high dimensional object, that's an image, and we would like to model a lower dimensional latent representation of the image. And so we can specify a deep generative model of the following form where our latent variable Zn is coming from a Gaussian, and then Xn given Zn is Gaussian, where the mean is parameterized by the output of a neural network. And here, theta hat represents parameters of the neural network that we have pre-trained to maximize the marginal likelihood. And so the problem that we'd like to solve is, given a new image x prime from the test set, let's approximate the probability of z prime given x prime using variational inference. And what we're going to then do is reconstruct the image by feeding the posterior estimate that we get out of VI into our neural network. And so here's sort of pictorially a visualization of these three methods reconstructing one particular image. And you can see from the bottom row that BAM is able to reconstruct the image much faster than the other methods. And a more quantitative measure of this can be seen through the mean squared error as a measure of image reconstruction error. And on the x-axis here, I'm now showing the wall clock time, and the y-axis showing the mean squared error. And the takeaway from this plot is that when we run BAM with a batch size of 300, it's actually converging faster than ADVI on any batch size. And the batch size is, of course, given by the titles of each panel here. So there's also many sort of extensions of this method that we've started investigating. The first is to high-dimensional latent variables. So in our earlier discussion, we were assuming that we can fit a full covariance with d-squared parameters. But if we want to go to much higher dimensions where d-squared is suddenly too expensive, we propose this sort of batch, match, and patch algorithm, where we now project our covariance update to something that's low rank plus diagonal. This is something that we call the patch step. And the resulting covariance update is now linear in D. And so we demonstrate this on a lot of large-scale, high-dimensional problems in a recent AI stats paper. A second extension one might be interested in is how can we use BAM if we want to do Bayesian inference with massive data sets where suddenly evaluating the scores becomes very expensive. So one thing you can do is use BAM with a noisy score computed from subsampling some data set. And so for future work, we're looking into evaluating the performance of using noisy scores within our batch and match algorithm. Finally, how can we use some of these ideas, but with richer variational families? So we would like to go beyond just Gaussian approximations. So this takes us to another method that we considered that proposes something called the orthonormal variational family. So here we're going to construct a variational family using a complete orthonormal basis set phi of k. And what we mean when we say orthonormal is that if we integrate any two of these basis functions, it's going to be 1 if they're the same and 0 otherwise. And so we'll consider the following variational distribution, where we're taking a linear combination of our basis functions and squaring them. And so here, these alpha coefficients are the variational parameters that we would like to fit. And additionally, we're going to impose a constraint on the alphas such that the sum of the squares of the alphas equals 1. So here, by squaring this linear combination, this ensures that our density is non-negative. And by ensuring this, by having this constraint on the alpha, it ensures that our Q is normalized. So this makes these valid densities. And so other properties of this family include we can generate IID samples from Q using a procedure that we describe in our paper. And we can also compute low-order moments. So this makes this family nice and flexible while keeping it tractable. And just to give you a sense of the expressivity, I'm going to show several examples of different basis sets. So the first one is coming from Legendre polynomials, where the black dashed line represents the target we're trying to approximate. And as the colors of the blue get darker, this is using more and more basis functions. So you can see it's getting more and more flexible. And you can see this with these other two examples of Fourier series and Hermite polynomials. And in particular, in our work, we actually focused more on this last case of Hermite polynomials because it gives us a way of modeling things on the real line, and the base distribution given by K1 is a Gaussian. And so this gives us a really natural way of extending the Gaussian case by modeling these higher order basis functions. So in higher dimensions, what we do is we just construct them via Cartesian products. So for example, in 2D, we now get a sum over each dimension. And again, we square this linear combination. OK, so what we do in ADVI, which is the following, we notice that when we try to minimize a score matching objective, this becomes equivalent to an eigenvalue problem. In particular, we're going to minimize an importance sampled estimate of the Fisher divergence on a batch of B samples. So it has the following form, where here the pi represents a proposal distribution from which we're drawing our sample ZB. And the second term represents the difference in scores between our variational distribution Q and our target P. And so when we go and minimize this estimate of the Fisher divergence, what we see is minimizing it over an order K orthonormal variational family is equivalent to some quadratic form with respect to a matrix M, where this matrix M is a function of the scores and gradients and evaluations of the basis functions. And so this just turns this into a minimum eigenvalue problem. So instead of having to resort to gradient-based optimization to minimizing these scores, we can now just solve an eigenvalue problem. So here are just some examples of applying ADVI in a couple 2D targets. So in basically the first column, I'm showing a bunch of different target distributions that are highly non-Gaussian. So the first one is a mixture of Gaussians, the second one is a cross distribution, and the last one is a funnel distribution. In the second column, I'm showing the Gaussian fit that you obtain from doing batch and match with the Gaussian family. And finally, the last three columns are showing ADVI with increasing numbers of basis functions. And so the basic message is the more basis functions we have, the better approximation we can get to the target distribution. We also looked at a number of hierarchical models in our paper. So here's just one example of the 8 schools hierarchical model. So this is a model where we have a 10-dimensional latent parameter, and the tails are non-Gaussian. And so I'm just going to visualize the posterior marginals of the even-dimensional coordinates. So in the first row, I'll show batch and match VI fitting a Gaussian. And it looks like the following, where here in gray, these histograms represent samples that we're getting out of MCMC, in particular Hamiltonian Monte Carlo. And the green histograms represent the variational inference method. We also looked at a normalizing flow. So this is fitting a more flexible variational family based on neural networks, and then trying to use SGD to optimize the elbow. And this is the result we get out of that. And you can see it fits this tail very nicely in the last panel. And finally, here we apply ADVI. And again, it sort of is able to capture this tail behavior much better than the Gaussian case. And so from a qualitative standpoint, we find that it sort of is able to do comparably to the normalizing flow. So just to conclude, we discussed several variational inference algorithms that minimize score-based divergences. These are black box in that they only require computing the score of the target. We first talked about a batch and match approach for full covariance Gaussians. And we find that this objective omits closed-form proximal updates. And those come from solving quadratic matrix equations. We then studied ADVI, which proposes an orthonormal variational family. And we find that minimizing a score-based objective there is equivalent to a minimum eigenvalue problem. And so there's a number of future directions that I'm very interested in. So one is extending our analysis of the Gaussian batch and match convergence. In particular, we'd like to apply it for finite batches and non-Gaussian families, or target distributions in particular. Another extension is really on the methodological side, especially for ADVI. We'd like to scale it to high-dimensional spaces, because the current sort of method suffers from a curse of dimensionality. And one other thing we're currently thinking about are sort of new batch and match style algorithms for other flexible but tractable variational families, including things like products of experts. And finally, I'm very interested in understanding the computational versus statistical trade-offs of score-based variational inference. So if you're interested in our work, here are some references. The first one is about how do we fit this full covariance Gaussian. The second paper is about ADVI. And then the final paper is about doing this low-rank update for the high-dimensional Gaussian case. All right, thank you.
Sort of, second order sum, and does that continue? Like, if you have like cortex sums in 4 dimensions, and
yes.
Okay,
so
does that sort of limit the applicability in higher?
In the,
yeah. Okay, and is there a way of like, in higher dimensions, maybe like truncating the like order of the sums, and I don't know, and keeping it tractable in some way in those dimensions?
That's certainly something you can do, but you have to figure out how to do that. So
Sure.
One approach we did here, which doesn't scale to very high dimensions, but it's essentially this like standardization approach. So let's make, here I can show it here. So let's make the base distribution as close as possible to a Gaussian. So this is in the Hermite case. And when you do that, you can find that you can actually fit things which, this basically lets you fit target distributions with much smaller numbers of components. And so I think there's more kinds of algorithms where you're trying to take advantage of the structure of the target. If there's some sort of low-dimensional subspace that we can plausibly model with a Gaussian, then maybe we don't have to use as much effort on the sort of non-Gaussian part of the subspace. Yes.
The button doesn't seem to be working very good. So if I could follow up on that question. So in many dimensions, you could generalize your expansion via something like a theorem. I don't know if you know about this, but there is a way to represent these high-dimensional things that you're trying to go for in terms of one-dimensional functions. It sort of looks a little bit like a feed-forward network where you have, something that looks like an activation of your expansion in terms of one-dimensional functions. You're sort of doing a little bit like that, but it is generalizable. Have you looked into that?
So we try to do like a factorized representation. So you take a bunch of product of expansions with respect to one variable, and you put them together. So this sort of sounds a little bit like what you're getting at. And in that case, there's not quite the objective itself doesn't nicely turn into an eigenvalue problem. And so there are other ways of trying to optimize that family, and I think there are kind of interesting things to do there. But we kind of, for this paper, kind of tried to focus on this eigenvalue perspective.